15 seconds. Guidance is internal. 10, 9. Ignition sequence start.
Space Nuts.
5, 4, 3, 2. 1, 2, 3, 4, 5, 5, 4, 3, 2, 1.
Space Nuts.
Astronauts report it feels good.
Hello as always, and thank you for joining us on Space Nuts, the astronomy podcast with Dr. Fred Watson from the Australian Astronomical Observatory, and I'm your host, Andrew Dunkley. Hello, Fred.
Good morning. I should really say good day, Andrew, because podcasts go out any time of the night or day.
That's right. People can listen at their leisure, which is the beauty of podcasting. Now, today, Fred, we're going to look at a few interesting things. The death plunge of the Cassini probe after its 20-year mission. We'll also take a look at something that Hubble has picked up, a pitch black planet, which sounds like something out of a science fiction movie. And we're going to maybe talk about this strange-shaped galaxy, and if we've got time, we'll squeeze in a listener question, a really good one too, so hopefully we've got time for that. But first up, let's look at the end of the Cassini mission. I imagine there would have been some tears at Mission Control as Cassini made its final farewell.
I'm sure there were, Andrew. I took time out on the evening of the entry of Cassini's entry into Saturn's atmosphere. It was evening our time here in Australia, so the actual impact, or it wasn't really an impact, it's just disintegration of the spacecraft, took place at actually about 9:57 in the evening our time. But for the hour before that, there was a live webcast from Mission Control at JPL, the Jet Propulsion Laboratory, and it was very interesting to me to see a room in which I had stood less than a month beforehand, because I visited that, and also to see some of the people there. And one person in particular who I met at JPL, Linda Spilker. We may have mentioned this before, we might have talked about this before, but I met her and I had a chance to have a chat with her. She's the Cassini mission scientist, so she has lived and breathed Cassini for, well over a decade and probably longer. And I said to her, so when Cassini enters Saturn's atmosphere and breaks up and then vaporizes because of its high velocity through the upper layers of the atmosphere, will it break your heart? And she said, no, it won't, because I'm already thinking about the next thing that comes after Cassini. And that's a reflection of just the amount of stuff that Cassini has shown us, particularly with regard to the moons Enceladus and Titan. And she, I think, is going to be working on something called ELF, and ELF is the Enceladus Life Finder. And the idea is to fly a probe through the ice volcanoes or ice geysers of Enceladus, and not just look for minerals and hydrogen and things which we've already found with Cassini, but to look for amino acids and lipids and things that might reveal that underneath the ice of Cassini there is an ocean which has living organisms in it. So she's already thinking about that, and I thought, well, that's great, a fantastic thing to say, but I thought, it sounded a little bit hard-nosed. But Andrew, on the day when the event happened, I could see on the webcast from NASA, Linda Spilker had a handkerchief in her hand. And she said to a reporter afterwards, it was like losing an old friend. Yeah. And I'm sure that's exactly what it was like. I can't imagine it being anything else. I mean, it was pretty emotional even from this distance.
Isn't it strange how humans can be so attached to what is ultimately an inanimate object?
Yes, that's right. But it's got a level of artificial intelligence on it, and more especially it has done everything that has been asked of it, and that you build confidence. It's like having a friend who will never let you down.
It's like saying goodbye to your old car. I remember when Mum and Dad sold a car that I practically grew up in.
Yes.
I was heartbroken.
Yes.
It was just a car. But back then it was a big,
had a name as well.
Well, it was a big part of my life. I'd been everywhere in the thing, so I can understand how it can affect people, and that's what makes us human, Fred. If we didn't think like that, we'd just be robots.
I think that's quite right. So just to wrap up, really, Cassini has revolutionized not only our understanding of Saturn, its rings and its moons, but really changed our thinking on maybe the way planetary systems evolve, what kind of environments we might find in planetary systems beyond our solar system, and perhaps more especially on ideas about where life might be and where it might come from. So some really stunning stuff has come out of Cassini, and I'm not surprised that people are really thinking ahead now to future missions, because there are going to be so many questions that we still would like to answer, even though Cassini has basically answered far more than everything it was ever expected to do. So you know, the mission was extended 3 times, Andrew. It was originally just going to be a 4-year mission in orbit around Saturn. It went into orbit in 2004, and it was extended 3 times. So
it's really a credit to the engineers and the technicians and the software creators to have something in such an environment last so long. I mean, I can't get a home computer to last more than a week.
Oh, well, that's because you're pretty rough on things.
I'm very rough indeed. So farewell, Cassini, and can't wait for the next one. You're listening to Space Nuts with Fred Watson and Andrew Dunkley.
Okay, we checked all 4 systems and keying with a go.
Space Nuts.
Now, Fred, the thing of science fiction that's come up in the news in the last week or so with the discovery by the Hubble Space Telescope of a pitch black planet. Now, I've seen a lot of science fiction shows and read a lot of science fiction books over the years, and these are always places of evil. What have we found?
Well, actually, its name is kind of threatening, because its name is WASP-12b.
Well, that does sound evil.
Yeah, WASP is actually a project that basically looks for planets around other stars. It's a ground-based project using relatively small telescopes. It looks for planets around other stars by watching the star's brightness and looking for dips in the star's brightness as a planet passes in front of it. It's a sort of common method for finding planets these days. It's one that's been relatively well studied. It was discovered back in 2008, I think. It has, the reason why it's in the news today is that the Hubble telescope has been used to make follow-up observations of the brightness of the star and the way the brightness of the star changes as this planet goes around it. So a couple of vital statistics, Andrew. It's about 1,400 light years away. So, of course, that's in our own galaxy, but it's not in our neighborhood. It's not in the sun's neighborhood. So this is a fairly distant one. This planet is known to be about twice the diameter of Jupiter. So it's a big planet.
Wow.
And you can tell that by the amount of light, the star's light, it blocks off when it passes in front of the star. And that gives you its size directly. And then the regularity with which this happens tells you what the year of this planet is. And this planet has a year of 1 Earth day. So it whizzes around its parent star, which unsurprisingly is called WASP-12a. So what the planet WASP-12b goes round once a day in our time. And that actually makes it quite easy to study, because you don't have to wait very long for it to pass in front of its parent star.
Yes.
But what the Hubble's done is something pretty neat, really. It's not just watched for the time when this planet is passing in front of its star and dipping its light. It's also looking out for the times when the planet is just about to go round behind the parent star, and just after it has appeared from the other side of the parent star. You see what I mean? As it goes around its parent star, it's going to be on this side and the other side. So half a revolution after it's crossed the disk of the parent star, it's going to be going behind the parent star. Mm-hmm. And so just briefly before that and after that happens, you've got the light of the star plus the reflected light of the planet itself, which is contributing to the starlight. So if you analyze that very carefully, it tells you about the brightness of the planet. And that's what this result or what this work has actually produced. A measurement for the amount of light, of starlight, that's reflected off the planet and it is incredibly small.
Which prompts so many questions.
Yeah, that's right, it does. So we know it's there because it blocks off the light of its star, but when it's on the other side of the star and contributing to the star's light, it's basically making virtually no contribution. We, in the world of astronomy, talk about something called albedo. And albedo is a Latin word meaning whiteness, how white a thing is.
Yeah.
In fact, so the albedo of a surface is how much light it reflects. So, for example, the moon's surface is actually quite a low albedo. The moon reflects about 12% of the light falling on it. Actually, if it was more like 50%, the moon would be nearly as bright as day in our skies. The moon looks bright, but it actually is not reflecting all that much sunlight.
Yeah, I mean, let's just ponder that for a moment. If the moon was an ice moon rather than dusty old basalt, our full moon nights would probably be quite, we probably have daylight.
We might even have to wear sunglasses.
Yeah, it would be very weird.
Yeah, very weird. That's right. So your point is absolutely well made there. But this planet has an albedo about half that of the moon. It's only reflecting something like 6% of the starlight that falls on it. And that is a real puzzle because we really don't know why it should be so low. The thinking is that with a hot Jupiter-sized planet or twice Jupiter-sized planet like WASP 12b, you would expect it to be a gaseous planet that has a much higher reflectivity, as Jupiter does. It's different from Jupiter, though, because this planet has a surface temperature of well over 2,000 degrees. I think it's 2,600 or thereabouts, something like that. So it's a very, very hot world, and that doesn't really tie with a very, very dark world.
Yes.
So I think the jury's out on why that should be, and some very interesting research. And maybe, Andrew, it is just because it's evil.
It could be just that. Yes. But it does. So do we know what it's possibly made of? I mean, we know a fair bit about closer planets. This one they've certainly been studying pretty closely too. But do we know what the formation is made of?
No, but we've got clues that come from the ability of the Hubble telescope not just to measure the light, but to measure the light in different colours as well. So that gives us an idea of, whether you're reflecting more light towards the blue end of the spectrum or the red end of the spectrum, and that is really it's the only clue that you've got as to what kind of things might be going on. But there are suggestions that there are some models that you can build of planets that have it's actually things that give you peculiar chemicals in the upper atmosphere of a planet like this, a gas giant, that actually absorb light. But the problem is that they only work for cooler planets than this one. This one's too hot for that mechanism to work.
Yeah, could it be something like there's an element in the upper atmosphere that
yes.
lets light in, but then as the light penetrates deeper, there's something stopping it from bouncing back out again?
That's exactly right.
Yeah.
There are sort of, they talk about clouds and alkali metals and things like that, but as I said, these don't work because it's got such a high surface temperature, 2,600 degrees Celsius, as I was mentioning. So it is, a big mystery. And
for the fans of Dune, we are talking, of course, about Giedi Prime. And if nobody understands what I'm talking about, I have no idea why. This is Space Nuts. Andrew Dunkley here with Dr. Fred Watson.
0G, and I feel fine.
Space Nuts.
Okay, Fred, now we're going to talk about the shape of galaxies. Now, there are so many galaxies out there, it's hard to count them. And, of course, we know what galaxies are. They're just big clusters of all that other stuff that, solar systems and gas clouds and you name it. But it would appear that they've been doing some work on defining their shape. And I would imagine because of the way the universe formed, there would be some form of consistency of shape. I mean, we do see anomalies from time to time, but have they come up with a basic formula?
So, well, yes, in a way, that's what's happened. This is a story that is fairly close to home for me because it, first of all, uses data from our telescope, the Anglo-Australian telescope at Coonabarabran. And secondly, it's been done, the lead author is actually a former colleague of mine at the AAO, Caroline Foster. She now works for the University of Sydney, but a lot of this work that she's done was done while she was with us at the AAO. And so she's used an instrument on our Anglo-Australian telescope. It's called SAMI. If I could remember what that stands for, I'd tell you. But it's basically, it's a machine that lets you look at the detailed spectrum, and that's the rainbow spectrum, which has this barcode of information in it, of several objects at a time, but in some detail. You probably remember that I've spent a lot of my career working on techniques using fiber optics, where you just use one optical fiber to pull the light off a star or a galaxy, and that tells you what its spectrum is. But you can also, if you're clever, and some of these people are pretty clever, you can build a machine that has maybe 60 odd fibers clustered around in a very tight bundle. So you can not just see a galaxy, a single measurement of a galaxy, but you can get light from every little bit of this galaxy. And you can do that then for many, many galaxies, that we call it multi-object work. And that's what SAMI does. So it lets you not only look at many objects at once, it also lets you analyze the detailed structure in each of those objects. And that is what Caro has done with a set of, if I remember rightly, I don't have the press release in front of me, but I think it's about 850 galaxies. And the problem that she's tried to address is how you tell what the true shape of a galaxy is. As you said, there are galaxies out there, the universe is full of them. We now estimate 2 trillion altogether in the observable universe. 10 a penny they are. And so, these huge aggregations of stars and gas and dust. But when we see them, we're kind of presented with a snapshot view, which means that, as a galaxy, maybe a galaxy as its shape, sorry, let me put it this way. As a galaxy presents different sides to you as it sort of moves around in space, that is almost certainly happening, but you can't, it's on timescales of millions or even billions of years. So what we see is this snapshot, and it means that you can never really get an absolute idea of what the shape of the galaxy is, because all you're seeing is one projection of it. You're not seeing, a three-dimensional view. And so galaxies we know come in different shapes and sizes, even the ones that have a disk like our own, which we call spiral galaxies. Some have got very fat spirals, some have got thin spirals, some have got loosely wound spiral arms, some are tightly wound spiral arms. They're just like people. They come in lots and lots of different shapes. So to cut a long story short, what Caro and her colleagues have done is basically used the SAMI instrument to measure the velocities of stars within the galaxies, which you can actually do with that kind of technology. And then by using those star velocities, they're able to infer what the true shape of the galaxy is and what its true, almost what its true dimensions are, because we get the numbers from the velocities. So a very nice piece of work. Once again, what we call survey astronomy, looking at many different objects, and actually one that I think will change our understanding of the way galaxies evolve.
Yeah, I like the description of the difficulty that astronomers face in trying to solve these problems. I mean, people would naturally think, I'm looking at a galaxy and what I'm seeing is its shape. But the description they give is that of a spinning coin. You flip a coin in the air and you can see its shape because of its revolutions.
That's right.
But what you're looking at when you look at a galaxy is a snapshot of the coin in flight, which doesn't define. It's impossible to define a shape. And so that's the problem. That defines the problem.
Yeah, and in fact, I was going to talk about the coin, Andrew, because it's a brilliant analogy for this, but I can't claim any credit for that because it's a journalist on the Sydney Morning Herald who put that idea together.
But it's a clever analysis of the issue, and it describes the problem greatly. So, defining an absolute shape for so many trillion things out there is very, very difficult.
Indeed.
All right. Well, we're on our way. Now, the shape of things to come on Space Nuts we'll answer one of your questions shortly.
Roger, you're loud and clear here also.
Space Nuts.
So, finally, Fred, listener questions. We've got one today which sort of looks back at the descaling, deorbiting, the destruction, whatever you want to call it, of Cassini, and it's a really good question and one we've pondered before. What would happen if one of the next Martian probes discovers life? With protection protocols in place, that would surely mean we would need to shelve any human exploration of the red planet, and I cannot imagine that it would be able to we'd be able to send humans to Mars and keep them from contaminating the environment with Earth organisms. So what's happening in that regard? There must be some sort of plan. Can you shed some light on this? That comes from Clem in Mornington. It's a good question and one we've pondered a few times in recent months because it is an issue.
That's right, Andrew. And Clem's absolutely on the money in saying that, yes, the Cassini spacecraft was deorbited. It was made to break up and vaporize in the atmosphere of Saturn in order to avoid any potential microbial contamination of some of Saturn's moons, which may have indigenous life of their own, which perhaps given a few billion years might develop into something quite interesting. Clem's question is, okay, we are looking for life on Mars, but we're also talking about sending astronauts to Mars. Probably in 2035 or so, NASA will send its first astronauts there. It seems pretty unlikely to me that anybody will get there before that, just because it is so hard, although certainly a few people such as Elon Musk have got ambitions in that direction. But the bottom line is, if Mars is such a sensitive place for embryonic living organisms, how can we justify sending a spacecraft full of humans who are basically full of living organisms, as well as being living themselves? How does that tally with what are called planetary protection rules? And the planetary protection rules are really strict in talking about how many microbial spores a spacecraft can legitimately carry to Mars without breaking the rules. It's a international protocols that actually go back 50 years. It's really quite remarkable stuff. It's a question that had occurred to me too. And as I mentioned when we were talking about Cassini, I spent some time, not very long, but spent time at JPL, the Jet Propulsion Laboratory, a month or so ago. And I actually asked one of the scientists there this exact question: how can we reconcile sending humans to Mars when planetary protection protocols really dictate that we've got to be very careful? And to be honest, I didn't really get a straight answer. With Clem's point, there has to be some sort of plan. Well, I'm sure there is, but it's not being terribly well enunciated, I don't think.
Okay.
So the answer I got was, we've got to wait and see what we do find. In other words, there are missions going to Mars, like there's NASA sending one called Mars 2020. ESA is sending the ExoMars mission, and these are specifically looking for life on Mars, not just signs of habitability, which is what Curiosity and Opportunity and Spirit have been doing, but these other ones will look specifically for life. So if they find any hint at all of life, present or past, on Mars, then I think that becomes a game changer for the way we see these planetary protection rules. Because if you then want to send humans to Mars with all their microbes, you've really got to change the paradigm under which you're working, because the planetary protection rules as they stand at the moment really basically forbid it. So I think we're going to go through a really interesting period, perhaps a decade or so, when some of this will be revisited. And there have been calls in the past to lighten up the planetary protection rules, and it may be that those calls will start to get heard in high places. So wait and see. I hope we'll be able to report on it in Space Nuts, Andrew.
Yes. However, it does bring in, and I'm sure Clem's already thought of this, the yes but question. What if, in all our probing with unmanned spacecraft and the like, we don't find anything, so we send people there and we go, oh, look, a frog. Yeah. I mean, that's a possibility.
Exactly. Well, Mars is a big place. Mars has more or less the same land area as the Earth has, even though it's half the diameter of the Earth. It doesn't have the oceans that we have.
But that is a distinct possibility. We'll find nothing, so we'll decide to go there, and then we'll find something, and of course all those protocols go down the toilet.
Yeah, that's right. We might try and clarify a bit more on that. I should, next time I'm talking to somebody who knows about... In fact, there's a good chance I might be able to do that tonight, because I'm talking to 2 astronauts tonight, NASA astronauts.
Oh, nice.
So I'll let you know. Okay. Yeah, Thank you very much, Clem. It's a great
space.
Question.
Yeah. It's like a science fiction show, Clem, that ends with a question mark on the screen. So that's where we're leaving this one. But thanks for your question. We appreciate it, and we certainly do encourage more and more questions, because they make us think, and they make Fred actually work for a change. Fred, thank you as always.
They don't call me Workaholic Fred for nothing.
Is that what it is?
It's a pleasure, Andrew. We'll speak next time.
For sure. That's Fred Watson from the Australian Astronomical Observatory. And from me, Andrew Dunkley, thank you so much, as always, for listening and following us and Facebooking us and Twittering us and whatever other weird things that we do in the Twitter sphere. Until next time, goodbye from Space Nuts.
Space Nuts. You've been listening to the Space Nuts podcast.
Mission complete, Houston.
Subscribe to the full podcast on iTunes, Audio Boom, and Stitcher, or your favourite podcast distributor. This has been another quality podcast production from Bytes.com.